Okay, welcome. In this video I'll discuss conservation laws and particularly how they apply to sharp discontinuities in flow called shocks. And these occur when fluid flow slows down from supersonic to subsonic. And this could be, for example, if the shock is moving, so if you have an explosion or a supernova, a shock is moving outwards into an undisturbed region. And so if you're in the frame of the shock, what seems to happen is that the fluid comes towards the shock and then passes through the shock, as we'll see, is compressed, heated, and then moves out. And so there's a sudden jump at the shock itself, which we'll see it can be very narrow indeed, where suddenly the velocities and the densities and temperatures all change over a very short region. As these discontinuous solutions, we can apply conservation laws to them to understand how they behave. These are called the Rankine-Hugoniot equations. There's a version for fluids, and we'll see in a later video one for plasmas. So it extends quite easily to MHD, but becomes much more complicated. But the simple case we'll see here is actually the same if you have a magnetic field straight through the shock. So in some cases, this also applies to plasmas. This set of equations implies some limits, which are important. So I'll just cover some of the important conclusions. Some of these are that there's a limit to the compression, so there's a maximum density ratio you can achieve with a shock, and this has implications for things like inertial confinement fusion, where you're aiming to compress some fuel. It turns out then this means you need multiple shocks to do that. There's also an entropy constraint to the shocks you find, and this means, for example, that shocks only occur in compression. So when a fluid is slowing down from supersonic to subsonic, not in expansion. So when you have a flow which is accelerating from subsonic to supersonic, then this is not a shock, and there's no discontinuity in that case, because if they were, then entropy would decrease. And so entropy provides a way of showing that shocks only occur in compression. So in previous videos we've discussed the conservation laws, and particularly of mass, momentum and energy. And in this video we're going to look at how these three conservation laws provide equations for the state of a system going across a shock. And so the way we'll draw this is we have a shock at this location here. Then we have fluid flow coming towards the shock, passing through it, and then passing out the other side. And so in these videos we'll always be in the frame of the shock. So you could, let's say, move into a different frame where the shock's moving, and for example the upstream was stationary, so this would be a shockwave moving outwards into an ambient fluid or gas. In this case we'll look at moving with the shock, so the shock is sitting still. We have a fluid flow coming in, so U1 is the velocity into the shock, density 1 and pressure, and then it passes through this very narrow region, and out the other side you have U2, ρ2 and P2, the state of the system or state of the gas after it passes through the shock. I say it'll turn out this is supersonic, and this will be subsonic. So the flow slows down, but the density and pressure increase. And this layer can in fact be very, very small. So it's obviously not zero in reality, but it can be very small. So it's typically of the order of the mean free path, because it's difficult to have changes in state much shorter than that, because the particles will simply move and mix together on that kind of time scale and sort of length scale. So mean free path. But for example, air. So we give some example of this. So air at sea level. So this lambda mean free path is roughly 70 nanometers. So the kind of shocks that occur over aircraft, for example, in air, are of this kind of order, sort of hundreds of nanometers, and so you end up with this really very thin layer where essentially the fluid changes very suddenly, and so for a very good approximation it can be treated as discontinuous. so a sudden jump. So now we're going to go through the three different conservation laws, so mass, momentum, and energy, and apply it to these equations. So how does U1, rho 1, and P1 determine U2, rho 2, and P2 as you go through the shock? Well, the easiest one is the mass, and the way to see this is that whatever mass goes into the shock must come out, unless there's any kind of ionization or creation of mass in here. Essentially, we always have that the flow of mass into the shock is the same as the flow out. And so, of course, the easiest way to write this is just that rho 1 times U1, which is the flow into the shock, is just the same as rho 2 times U2. And a way to kind of derive this would be to write down the density equation in conservation form. So you have d rho by dt plus this divergence of rho u. So this would be the conservation form. And then, since we're moving in the frame of the shock, so the shock is stationary, this is steady state. So assume that the incoming velocity, for example, is not changing, the incoming density is not changing, it's just the shock is stationary, and so this goes to 0. Then we have the divergence of this is 0, and so conceptually we integrate this across the shock, because obviously the gradients here are infinite, but we integrate say from minus delta over 2 to plus delta 2, where delta is some small distance one side of the shock to the other, and then let limits of this width go to 0. And so we integrate this derivative, and it just ends up being the jump in these quantities. And so the end result is just saying that says the gradient of this must be 0, so therefore rho u is constant, which is the same as what we have here. So for more complicated equations, you can write it in this form, and then think about doing this integration and limit. But often it's just a case of saying whatever's in this here must be constant, and so therefore we can write this equation. That whatever's on the left-hand side is the same as whatever's on the right-hand side. Okay, so that's the first equation for mass. Then we'll go on to momentum. In some cases, the more complicated or most complicated equation, because it's a vector equation. Here we're keeping it quite simple, so the flow is just perpendicular to the shock. In general, you can have oblique shocks, but for fluids, actually, it's not too bad. MHD, it gets quite a bit more complicated. Again, the trick is to write things in conservative form. I.e., in terms of divergences of fluxes. So we can write d rho by dt of rho u is the momentum or momentum density, and here we have the flux of density. It's given by the pressure. So here's a tensor, so this is our density matrix. So plus then rho u is the direction of momentum. And here, if there's no viscosity or any other things, then this is just 0. And so again, the same argument applies, that this goes to 0. Whatever's in this bracket, this must be constant. And now we can take different components of this. This is a tensor, so it has two indices. We'll just take the components of u perpendicular to the shock. And so this just gives the basic pressure, P1, so on the left-hand side, the upstream supersonic part, plus here we have rho 1, U1 squared. So this is on the left-hand side, and that's just the same as on the right-hand side. So that's the second equation. And worth adding here that this equation also appears in plasma physics, so in scraper layer particularly, where this is one of the components used in something called the two-point model, which is quite a widely used both experimentally and theoretically, because it essentially relates the pressure to the fluid flow at any point, and so the total pressure is conserved along field lines in the edge of a tokamak, or to a good approximation, and so this provides a good way of thinking about this. This is essentially the total pressure, or sometimes called total pressure, and then this is sometimes broken up into two pieces. So P here is the static pressure, whereas this is the pressure you'd have if the fluid wasn't moving, and then this is called the dynamic pressure. Or sometimes called the ram pressure. So this is the momentum imparted by the moving fluid. So it's the fluid being thrown against the surface. So if you're measuring, think about pressure as being putting a plate in the flow, and measuring the force that's measured on the plate. The pressure is just the fluid sitting next to the plate. Has a temperature, has a pressure. The individual particles are bouncing against the wall, exerting a pressure. The second term, the ram pressure, is the bulk fluid is being pushed against the plate, and so this provides an additional force due to the movement of the fluid. And so there's static pressure, dynamic pressure, and added together makes the total pressure. Okay, so then finally we have the energy conservation. And this we can again write in conservation form. So write the energy density as E, so like energy density. I read this in a previous video, so again we can write this in as a conservation law. And here this is the energy flux. It's a combination of the advection of the energy in turn with the pressure. So here the energy density is given by a combination of the internal energy, which is the pressure, so this 3 over 2 here depends on the ratio of specific heats. This is for a monatomic gas, and then plus the kinetic energy, so half rho u squared, that's kinetic. Okay, so then the same way, this goes 0, this is constant, and so we just essentially add P here, so this becomes a 5 over 2, and then this whole thing times U is also constant, and so therefore we end up with, which here I've taken out a factor of rho U, so here we have rho U here, so taking out this factor, and that gets divided by rho in this factor here. Now rho U is itself also constant. So remember, this is the first equation we derive, this is constant. And so therefore this part in the brackets here must also be constant. And this, if you've seen this before, this is Bernoulli's equation. Which is quite widely used in fluid flow, or incompressible fluid flow. So again, it gives things like the relationship between the pressure and the velocity as a function of the distance along a streamline, for example. So think about fluid flow past an aircraft, the change in the velocity is associated with change in pressure. And so this of course just gives us that 5 over 2, so P1 over rho 1 plus a half U1 squared on the left hand side, and then on the right hand side we have the same thing but just different indices. So rho 2 plus a half U2 squared. So this, again, the supersonic left hand side and the subsonic right hand side. So now I have 3 equations with 3 unknowns, which I can write out here. So these 3 equations and 3 unknowns, which are rho 2, U2 and P2. So if we know the state of the fluid before the shock, so rho 1, U1 and P1, these 3 equations are enough to constrain the 3 unknowns of rho 2, U2 and P2, so the shocked fluid after the shock's gone past. So in principle, these give a unique solution. They're nonlinear equations, so this can have some surprises. But essentially, we have 3 equations, 3 unknowns, so we can find a solution. Okay, so I'll just quickly cover 2 important consequences of these equations. So these here, there are a lot of calculations that follow from this. I won't have space to go through them just now, but if you look up textbooks, you'll easily find these solutions. So the first one is that shocks must occur in compression, and then also that there's a limit to the compression that we can achieve. So maybe if I just cover the limits to compression. So you can derive an equation for the ratio of the upstream to the downstream velocities, and then because u times rho is constant, this then is just related like this to the densities, and this is just the ratio of the density of the downstream after the shock to the density upstream. And by manipulating these equations, you can end up with this equation where m1 is the Mach number, so it's the ratio of the velocity, so it's the velocity of u1 divided by the speed of sound in the upstream region. So it's how many times past the speed of sound is the fluid flowing, or the shock moving into the fluid, for example. Well, the interesting thing though is that if you make the shock stronger and stronger, so you make the Mach number extremely high, so as m1 basically goes to infinity, so you make the strongest shock you can produce. This tends to a limit. So in that limit, of course, this 2 disappears, these m1s cancel, and you just end up with a ratio of this gamma plus 1 divided by gamma minus 1. So we end up with rho 2 divided by rho 1. This goes to gamma plus 1 over gamma minus 1. So there's a maximum limit to the density you can achieve. And so if gamma is 5/3, for example, then we end up with a maximum of 4 for this. And so there's a maximum density compression. So instead of compressing the plasma, what stronger and stronger shocks do is heat the plasma. So they generate more and more entropy. They end up heating the plasma, and the pressure keeps increasing. So the pressure of the downstream plasma can increase and keeps increasing as the Mach number goes up. But the density does not. The density saturates at a maximum of about 4, or depends on what this gamma is, but for monatomic gases. And so therefore you can need multiple shocks if you want to compress beyond just a factor of 4. So for example, in ICF, so inertial confinement fusion, if you want to compress a capsule of fuel to very high densities, you need multiple shocks rather than just a single one, because one is limited by this ratio here. The other I mentioned is that the entropy limits or constraints on shocks, and this you can get by writing down the entropy of a gas is the specific heat at constant volume times the log of the pressure divided by rho to the gamma, plus of course some kind of constant. And so you can use this to then write down what the change in this quantity, so change in S, so we're going to write this as delta S across the shock. So by doing some calculations, you can essentially write down what this is in terms of delta S, for example, the difference between these two. So we have just a CV, then have basically the log. So we have P2 over rho 2 to the gamma minus log P1 over rho 1 to the gamma. Essentially, you can plug these in the equations above, and then you can try and work out whether this is positive or negative. So obviously, we must have delta S greater than 0 or equal to 0, or otherwise we'd have a reduction in entropy, which is forbidden by thermodynamics. So there's several different ways of showing this. One is to basically calculate the derivative of S with respect to the Mach number. And so you can show that d delta S by d Mach number is actually 0. At Mach number is 1. So try and look at whether you're at the sound speed. If you go above the sound speed or below the sound speed, how does the entropy change? You can actually see the second derivative, so d2 delta S by dm1 squared is also 0 at this location, but the third derivative, so the third derivative of the entropy with respect to the Mach number is actually bigger than 0 at m1 equals 1. So what this means is that as the Mach number increases past above 1, then delta S is bigger than 0. So if m1 is bigger than 1, delta S is bigger than 0. And if m1 is less than 1, then delta S is less than 0. And so of course this second case is forbidden. And so therefore the Mach number going into the shock must be bigger than 1. So you must have compression, and there are no shocks in expansion, because otherwise the entropy would drop